looked at what I called infinite limits. And what that was is when the y values approached infinity, such as at a vertical asymptote. When the y values get increasingly bigger, either in the negative direction or the positive direction. But what if we're not talking about the y values approaching infinity, but what about looking at when the x values approach infinity? So just like when you made a table and you were looking for x values that get really, really, really close to 2, I'm looking for x values that get really, really close to infinity. So there's a couple of approaches to this. You can actually plug in numbers that are getting really, really close to infinity. So like, 10,000, 100,000, and so forth. So I think I showed you on both Desmos and on a graphing calculator that you can set up your table where you can type in numbers. So I'm gonna do that. I'm gonna go to y equals, and I'm gonna put in this equation. Now there is a shortcut for this, and I'll show that to you in a second. I'll show you actually a couple of different ways to do it. So I have mine set up on ask, so it's going to ask me for x values. So I'm going to start with 1,000, and then 10,000, and then 100,000. Why would it just go ahead and jump to 3? So 2.995, 1000000, and I just can keep putting in. It's saying it's approaching 3. And if I look at the graph, I'll see that as x approaches positive infinity, my graph is leveling off at 3. That was called a horizontal asymptote. This means, so I'm going to look at the graph again, at 1, 2, 3. So I have, I'm going to try to mimic the graph as much as I can. It does something like this, and then this side's doing something like this. I have this horizontal asymptote. It's a line that the graph approaches but doesn't cross at the edges. There's a horizontal asymptote at y equals 3. Now I told you I was going to show you other ways to think about this. Well, the other way to think about this is if I'm letting x get super, super, super big, like billions, 1 billion, does subtracting 2 really affect a billion? Or would multiplying by 3 affect it more? The multiplication affects it more than that subtracting. Just subtracting 2 from a billion, it's still close to a billion. Adding 1 to a billion really doesn't matter. So one way you can do this is to kind of just think about what would affect it. Well, the -2 and the +1 really don't affect it. It's just going to be the variable. So 3x divided by x is 3. Now what about this one? Again, if I'm looking at when x becomes super, super, super large, like a billion or a trillion or a quadrillion or something, is subtracting 1 going to matter at all? Is adding 1 going to matter at all? No. This x squared is going to be the most important thing. So an x squared divided by an x squared is just going to leave me with 1. So I would have a horizontal asymptote at y equals 1. Now there's, let's look at this one. This is going to be a little different. 1 divided by x. So even if it's x squared, x cubed, x to the fourth, whatever that is. So x to any power. If I'm dividing 1 by a really big number, what is going to happen? So I really want to play with this idea and show you what's going to happen. So I'm going to do 1 divided by x. Let's just do 1 over x. And if I'm looking at my table, I get 0.0001. Then this would be 0.00001. Then 0.00001. And it keeps getting 1. It's getting super, super small. That's point, and then there's 10 zeros and a 1. This is getting super, super small. Look at what happens on the graph. It gets really, really close to the x-axis. This approaches 0 every single time. So when the denominator is bigger, it's going to approach 0 every single time. And there are ways to use that to kind of prove some of these other ones, and you'll see that in textbooks. I like to just remember if the denominator is the bigger one, then it's going to go to 0. What's going to happen if I have and I'm going to actually use this definition to prove this one. Now, if you remember some of the shortcuts, if we looked at the leading terms from the numerator and the denominator, just really focusing on x squared, because that's going to be much, much bigger than just an x and way, way bigger than just a 2 or a 1. If I just looked at that, I'd end up with 3 over 5. I want to prove that that is the limit as x approaches infinity. So what I'm going to do is I'm going to divide the numerator and the denominator by the highest power of x. Just bear with me. So if I divided the numerator and the denominator, so if I divided the numerator by 1 over x squared, if that had been a cubed, I would have used a cubed. And then this by 1 over x squared. Let's see what we get. And it's going to get a little messy before it gets prettier. 3x squared over x squared minus x over x squared minus 2 over x squared. You see what I did there? I distributed. 5x squared over x squared plus 4x over x squared plus 1 over x squared. The limit as x approaches infinity. Okay, so let's see what happens to each of those terms. 3x squared over x squared becomes a 3. This is going to become 1 over x, because this x will cancel out with one of those, minus 2 over x squared. Then I'll have a 5 plus 4 over x plus 1 over x squared. Now remember this kind of rule. If I have x in the denominator and x is approaching infinity, it's going to go to 0. So all of these that have a 1 over x or 2 over x squared are going to go to 0. This is going to become a 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 0. All I'm going to be left with is 3/5. So the limit is 3/5. That is a proof of what I kind of do, just, kind of with my mind. I'm only looking at the ones with the largest exponents, and I just kind of, everything else is going to go to 0. So 3x squared over 5x squared leaves me with 3/5. But this is the longer way of doing it. Let's do a couple of other ones. Let me find a good one. I want to do a little bit of a different one, and I apologize for the pause here in the video, but I'm trying to find a good video, a good one on the infinity thing. Oh, I guess I didn't write it down. I really did it in class. The limit of, we're going to do as x approaches negative infinity this time. Of the square root of 4x squared plus 1 over x plus 1. This one's a little different. And we could always put this in the calculator and see what ends up happening. But I'm going to show you a different kind of way to think about it. Now, I would never say equals out to the side on this, because this is just the way my brain works. And if yours doesn't work that way, then that's okay. All right, the plus ones aren't going to matter, right? So I'm left with the square root of 4x squared over x. Two x over x. Now, we've got to think about, when I take the square root of x squared, what's going to end up happening there? Well, this is going to end up being negative, because this x was negative. So I end up with -2. Let me prove that. Square root of 4x squared, plus 1 over x plus 1. Let's look at the graph of this one. Do you see how it's going to -2 over here? But if I were approaching positive infinity, it approaches positive 2, because we still have this 2x over x, but when we're looking at negative infinity, the square root of x squared is going to be negative. Remember, with all of these, you can double check with your calculator or by plugging in points.